All right, entice some of you here with the promise of lunch. We're starting the seminar now. Chop chop. Okay, we're very fortunate. We've had a bunch of talks this week by our friends in the GMT collaboration. One of our friends who's been here all week is Professor Michael Brown.
Not professor.
Not professor. Oh, I'm sorry, they do it differently. So down under.
Commonwealth system, yeah.
Okay, well, he's traveled all the way from the southern hemisphere, so that's why he leans over on one side so much.
The Coriolis course.
But he's a friend of mine. We knew each other as we were both postdocs in Tucson, Arizona for a while before you left for Princeton. Was that the Spitzer Fellowship?
The Henry Norris Russell.
The Norris Russell. The Norris Russell Prize Fellowship at Princeton University before joining the faculty in Monash University. He's been a friend of mine for a while. He's been doing some really interesting work on new measurements of multicolor observations and spectroscopic observations of galaxies. I think that's what you're going to talk about today, Michael. So thank you.
Thank you, Casey. Before I get started onto sort of the body of the talk, of course, like much of astronomy today, it's done in collaboration with a large number of people, many of whom I actually hadn't met before I started this project. I think I've only got Master and Manishi to go now, so I get to meet in person. Scattered around the world, most of them came on board via email and have made some contributions to this work. I did find people to collaborate with in South America and Antarctica, which was an oversight on my part. Much of this research is like research around universities worldwide is done in a building of architectural merit, which probably polarizes people. But we're very happy to have a building that represents the 21st century rather than the 1960s. Also in this work, in this talk, I'm going to be mentioning the work of some Monash Postdocs and PhD students, notably Richard Baer, who is just working on his thesis corrections now, and Samantha Penny, a postdoc who will be moving to work on the Manga survey at Portsmouth a little later this year. So central to this talk and this science is an atlas of galaxy spectra, which has consumed a large fraction of my scientific life the last couple of years. And there's a couple of reasons why we need atlases of galaxy template spectra. So one is just to determine luminosities and absolute magnitudes for galaxies beyond the local universe. Even if we have good redshifts, we're typically observing with filters that don't actually match the rest frame filter that we're interested in, and so we need some model of the galaxy spectrum to go from our observed observations to the rest frame wavelength of interest. It's also useful to have galaxy template spectra for determining photometric redshifts. With the large mosaic surveys now and LSST in the future, you're not going to be able to obtain spectroscopic redshifts for large numbers of galaxies. And so it's critical that you have reliable photometric redshifts. And if you're going to get reliable photometric redshifts, it helps to have reliable models of galaxy spectra.
I want to ask you about it, because I know when we were working on physics in Tucson, you were doing like photometric redshifts, and you can never match red galaxies in particular with any kind of existing template.
Yeah, it was.
So this is born out of some of your frustrations.
Yeah, it's been born out of more than 10 years. It's been born out of about 14 years of frustration. And for a while there, I could sort of sit around as a postdoc and imagine that someone else was going to do the job and make an updated version of Galaxy SED templates, and I could wait a while. But then my graduate students started doing this science, and this was starting to affect their work. And there's no way I'd let unleash a project like this on a poor graduate student, because it relies on a lot of background knowledge. And so I bit the bullet and did it myself so that my graduate students could do their science.
Very altruistic.
I just got sufficiently annoyed that I had to do it. Anger is an excellent science motivator. Local analogues of high Z populations is also very useful. So if you want to interpret limited observations of a high redshift object, it can be useful sometimes to have more detailed observations of a lower redshift object. It's also useful if you want to measure the evolution of a population to actually know what the properties of the local population are. And as I'll get to a little later in the talk, there's some interesting examples of where that goes wrong. Star formation rates. If you want to calibrate star formation rates, you want to bolt some star formation rate indicator to usually dust-corrected H-alpha measurements. And so you need a spectrum that covers the relevant wavelength range for the star formation rate indicator, perhaps 24 micron observed at a series of redshifts, and so you need a spectrum. Now, these questions can be answered with template spectral libraries, but there is, of course, the question of why not address them with models, since models, at least hypothetically, could produce sort of noiseless spectra, and they have a series of derived properties that just pop out for the models, things like stellar masses, instantaneous star formation rates. But the models do have a number of limitations. So a lot of the models, at least until recently, didn't include PAH emission in the mid-infrared, which matters if you care about the Spitzer bands. Many of them don't have nebular emission lines, which generally isn't a big deal, but can matter for some galaxy populations, such as the ones that Casey worries about. And they often have simplified dust geometries and simplified star formation histories. So if you're modelling a galaxy, say like this, it might not have a simple exponentially declining star formation rate history, and it might not have a dusty screen as its dust geometry. And so this being the case, it's useful to have an empirical spectrum that you can use for galaxies such as this. Another issue with models and also with, say, fitting principal component spectra is sometimes you have a very limited number of observations, say a couple of photometric data points, that you're trying to fit with a galaxy model that has to have a lot of information built into it, star formation rate history, dust, the PAHs, etc. And so you might not actually have enough observational data to constrain a very complex history for that galaxy. And so that being the case, it's useful to have a template that sort of by definition matches the real spectrum of a galaxy. And it should be noted that what I present today is in press. I just sent off the proofs yesterday afternoon. Now, there are problems with the atlases of template spectra that have been available over the past few decades, although they do a superb job, or have done a superb job over those decades. It's Common, Weidman, McKinney, 1996 templates, and the Paletta template, for instance, more recently. So one of the problems with the current set of template libraries is illustrated here with this plot from the Deep 2 Galaxy Redshift survey. I'm glad I didn't throw this plot up when Jeff was here earlier in the week. What this plot is a plot of rest frame colour versus absolute magnitude for a series of redshift slices. And you can see that the bimodality, the red and blue galaxies, and you can see that as a function of redshift. Now there's a problem with this colour magnitude plot, and it's a really significant problem. Can anyone spot what that problem is?
Casey knows.
That's not necessarily the problem.
Is there a selection bias? Is there a selection bias?
There certainly is a selection bias, but that should be modelled. The interesting thing is the colours of the red galaxies, which should be passively evolving. If you look at the colours of the red galaxies as a function of redshift, despite looking over several billion years of cosmic time, the colours remain the same. They don't change. And that just can't be right. Okay, so you've spent a lot of Keck nights. I suspect the Deep 2 Galaxy Redshift survey might even be measured in units of Steidels, not millistidels, but actual Steidels of Keck time. And yet,
The observations here, how they select their red and blue galaxies, how they measure their luminosity functions, have errors that are quite possibly on the order of tenths of a magnitude that are probably introduced by their K corrections and from the photometer, from the K corrections. So that's a big deal. Another problem is the photometric redshifts illustrated here. Now we've seen much better photometric redshift plots. This is me just chucking some photometric data in and running some photometric redshifts, and it's a very simple chi-squared fitting code, and I know there's better codes out there, but it's simple and it illustrates the point I want to make. So what we can see here is that when we get to low redshift here, it's an absolute mess when it comes to the photometric redshifts. It's absolutely horrible. And the reason why it's horrible is because I added in more data than normal into the mix. Instead of just doing optical in the infrared, I threw in the mid-infrared as well, and everything went horribly wrong. Now, normally, when you add more data to constrain a fit, things should generally get better, or at least not grossly worse. And so this is, again, an indication that something is wrong. So let's have a look at sort of what is wrong by having a look at the errors of the SED templates. So what these plots here are color diagrams for a couple of redshift slices, and in grey I'm just showing the observed colours of galaxies taken from the AGES survey, and this is just observed colours, so no K corrections. And in grey we have the observed colours of galaxies, and then overplotted with the red dots, the colours synthesised from the Coleman-Woon-Weigman templates and the Kinney templates. And I should say that these templates are decades old, so given the limitations of the data available at the time, they do a remarkably good job. And that should be clear from this. That should be remembered when I'm discussing limitations of these templates, because they're limited because there were lots of limitations with the data available at the time. Regardless of that, if you look at the galaxy locus and you look at where the templates are, there's systematic offsets. There's a template up here that's just off the galaxy locus entirely, and the Kinney templates seem to sort of be underneath the observed galaxy locus by several tenths of a magnitude. The Coleman-Weigman templates, which are commonly used, sort of arc sort of the wrong way. They're going this way rather than that way around the galaxy locus. And those errors are several tenths of a magnitude, so they're larger than the random photometric errors that you would get on the photometry for these faint galaxies at significant redshift. The same is true even for more contemporary templates. So these are the Paletta templates that have been used reasonably extensively in recent years. An optical color diagram on the left, a mid-infrared color diagram on the right. Similar problems in the optical to the Kinney templates and the Coleman-Weigman templates. In the mid-infrared, it gets even more interesting. So we have in the mid-infrared sort of two clumps for the observed colours of galaxies. Elliptical galaxies, early type galaxies here, which have roughly Rayleigh-Jeans spectra. And then over here on the right are the galaxies with the strong dust emission and PAH emission. Perhaps not unexpectedly, there's quite a few templates that do match the Rayleigh-Jeans spectra of galaxies, but over on the right, the locus of the star-forming galaxies isn't really populated at all. The star-forming templates are really all over the place. And this explains why I was getting those big photometric redshift errors before. There's big mismatches here of several tenths of a magnitude between the observed colours of star-forming galaxies and what the mid-infrared templates produce. So I wanted to fix this, particularly for my grad students had to complete their PhDs. So the approach that I took is there's lots of data out there, relatively big data. It's an ambiguous term, we can argue about it later, but there's a wealth of great data out there online, and some of it that various people in this room have probably sweated on at various times. However, the catch is that if you need to use it, and this is maybe for the grad students, you do need to have a good look at it, ideally all of it, and you need to look really hard at what's producing your outliers. And that's been a very worthwhile experience, if a little tedious, in producing this atlas. It's also been extremely useful in producing this atlas to have redundancy in the data. So having multiple sets of data with their own esoteric systematic errors and being able to cross-match and see what's going on. So for instance, being able to cross-match the Swift U-band with the Sloan U-band has been very, very useful. Being able to compare Ys and Spitzer 4-ish micron data has been very useful, and the Ys and 22 micron data and the Spitzer 24 micron data that's been very, very useful comparison. And again, critically, maybe the statement to graduate students is it's really, really useful to talk to the relevant experts. They're always happy to hear about your research, and they're usually very, very happy to share their expertise. You can normally contact them via email. So I really didn't know anything about Akari when I started this project, and it was not hard to email someone who's done a lot of work with Akari Spectra, bring them on board and get lots of useful advice on how to deal with Akari data. Well, originally I was intending to just do a replacement of Coleman, Wu, and Wiedemann or Kinney with 12 templates. It kind of grew and ended up being 129 bright galaxy templates, all of which have large aperture spectrophotometry, the bulk of which was collected by Rob Kennicott and by John Mistakis during his thesis, where they did optical drift scan spectrophotometry. So they slid the long slit up and down the galaxy multiple times, so they got an integrated spectrum of the galaxies in question. It's an amazing data set that must have taken Lord knows how much bleeding to get together. There's then
1,000 million stars.
On that order, yeah. Spitzer IRS spectra for the bulk of the sample, so almost all of the galaxies, at least the ones that don't have Rayleigh Jeans, SEVs and the mid-infrared, have Spitzer IRS spectra. Lots of data from the SINGS program, lots of data from GOALS, but also data just taken from the archives. And then for around about, I think it's about 40%ish of our galaxies, we have Akari spectra. Akari doesn't have that high a profile depending on which community you're talking to, but it was able to obtain spectra between 2.5-ish and 5 microns, which has some very interesting features in it, particularly when you get to ULERs. And then a critical feature is having matched aperture photometry in 26 bands from Swift, Galax, Sloan, TUMAS, Spitzer and Ys. And that wealth of well-calibrated data over a broad wavelength range really wasn't available in previous decades. And it's incredibly useful to have matched aperture photometry over a really broad wavelength range if you're trying to bolt different spectra together. And that's been really critical to the success of this project, and one of the reasons why previous template libraries have had errors, I suspect, is almost certainly because it's difficult to match spectra together taken in different wavelengths that don't have precisely the same extraction aperture. It's a real issue. The redundancy of data has allowed us to model a couple of things, including errors in the Ys 22 micron filter curve, which actually is probably closer to a 23 micron filter curve, and Swift coincidence losses. Swift detector operates like an X-ray detector. It has photon coincidence losses, and those haven't been well defined for bright extended objects before. Foreground dust extinction using Planck data and a new dust extinction curve from Josh Peake. The Planck data does differ from the older dust extinction maps, including high galactic latitude. And then Elizabeth DeCuna has provided the MagPhys code, which has been superb for modelling the gaps in our spectral coverage. So here's just one example of one of the galaxies that we looked at for the project, R256 South, and the various apertures that we used to extract the data. So the white box here is the aperture that we use to extract the photometry across all the wavelengths and the optical spectroscopy. And then in blue, green and yellow are the apertures that we use to extract the spectra from Akari and Spitzer in the short mode and Spitzer in the long low modules. And the apertures obviously clearly don't precisely match, though at least for this galaxy they do capture a large fraction of the total flux. And you can imagine just it's relatively easy to renormalize those spectra using the matched aperture photometry and get something that's very close to the true spectrum. Another one of our galaxies, something much more local, with the extraction apertures shown. We didn't have a Kari spectra for this particular galaxy. This aperture looks relatively small, but we do still get actually a significant fraction of the infrared flux at the relevant wavelength. One of the blue compact dwarfs in the sample, which these galaxies have proved particularly tedious because they've got very low signal-to-noise Spitzer spectra. For a lot of our Spitzer spectra, we're looking at Spitzer maps where they've moved the slit around the galaxy to construct a data cube. But for some of the more compact galaxies, we just have spectra where the Spitzer stared at the galaxy in question. But for some of those observations, we extract a large fraction of the flux and we can produce a reasonable SED for the entire galaxy. Because we have the redundant data, including Spitzer 24 micron, Spitzer peak up imaging, and we have the Spitzer IRS spectra, we've been able to find some interesting errors in the data. And one of the most interesting errors is an error in the WISE 22 micron filter curve, which has been identified previously but not particularly well measured. And the nature of the error is that if you have a spectrum which is rising towards longer wavelengths, the the WISE 22 micron data overestimates the flux. And in the case of some of the more extreme lurgs and U-lurgs, it's overestimated the flux by as much as 30%.
It's just calibrated with a black body type curve instead of a rising spectrum.
It's calibrated with a black body curve, but their filter curve is in error, and so it is a filter curve error. So because they calibrated with a black body for objects that have Rayleigh-Jean spectra, by definition the calibration is spot on, but then the error builds up as you go to things that differ from a Rayleigh-Jean spectrum, and the more it differs, the larger the error. So if you just have some simple approximation of the spectral slope, you can measure the error as a function of spectral slope and get a nice correlation there. And to first order, that error is what you would get if the WISE 22 micron filter curve was actually a 23 micron filter curve. So that's quite significant. And it's not necessarily unexpected because the WISE 22 micron filter curve on orbit did not perform in the way expected. It was not nearly as sensitive. Something wasn't quite right with that particular band. So the whole process was repeated for 129 galaxies, which took a while. And then with the photometry, you start to get some interesting results. So this plot's just the optical color diagram of the Sloan filter set for nearby galaxies. We've color-coded the objects by their RC3T type. The red circles correspond to elliptical galaxies, the green stars, light-type galaxies, and then the purple squares don't have classifications, but a lot of those are peculiar and irregular galaxies. And then they're overlaid on top of the colours of Sloan galaxies in grey. They don't perfectly match up, in part because we're doing aperture photometry, whereas Sloan's using their model fit photometry. And so it's not quite comparing apples with apples in this comparison. One of the things that's quite interesting here is that the locus of elliptical galaxies is actually slightly offset from the locus of star-forming galaxies. This is something that's sort of been seen before when you look at optical and infrared colours, but it doesn't normally show up in the optical. And it's quite interesting because normally people sort of assume that the galaxy locus is just a banana and you can sort of define it with a couple of points and then interpolate, and that's not the case. The elliptical galaxies are offset from the star-forming galaxies. It's also interesting that, say, down here, while there is a locus of disk galaxies, that there are galaxies that are genuinely lying off this locus. Often things that are sort of have Lurgy type properties are down here. Some of the galaxies up here are things like post-starburst galaxies with strong Balmer breaks. So you're already seeing some diversity here. There's this big fan of galaxies down here that's not normally seen in color diagrams. These are the blue compact dwarfs with the really strong nebular emission lines. And those nebular emission lines are in fact so strong that they affect the broadband galaxy colors. And we're able to check that because we've got spectra for our galaxies. So what we can do is we can take the emission line fluxes and subtract them off the photometry and see what happens. So we go from something that looks like this, and we subtract off the emission line fluxes, everything collapses towards something that's more like a locus that you might expect if you were just looking at the galaxy stellar populations and dust extinction.
Well, you said Ritchie sequences, right? I mean, I like you mentioned the optical and near infrared comparison, because there you use the two sequences. The star-focused sequences are more of
A passive sequence.
yeah.
Yeah, so that passive sequence is still there. You go to other wavelengths and you see more diversity. Again, this isn't necessarily particularly new. There's been Galax ultraviolet color diagrams floating around for a while, but lots of diversity here. In the elliptical galaxy population, you have a broad spread in UV colours, which is the UV upturn, which has been known about for several decades. But sort of the point here is that if you're trying to model galaxy colours, maybe having only one or two elliptical galaxy templates is not a good idea. Okay, it's simplifying things a little bit too much. There's sort of a little bridge over here to the star-forming galaxy population, which then sort of narrows down as you go to progressively bluer colours, and then you have some dust-obscured lurgs here, and in fact there's one or two that are sort of off the top of the diagram there. In the mid-infrared, you have actually quite a split between the early type galaxies with Rayleigh-Jean spectra here and the star-forming galaxies over here. There's really very few objects that we could find that would fill the gap here. So even with 129 galaxy SEDs, we're not fully filling the parameter space. And then up here we have AGNs, and we also have some low metallicity star-forming galaxies with hot dust and weak paths. So lots of stuff going on here that you can't necessarily approximate with half a dozen templates. We can use our photometry to renormalize our spectra and bolt it all together. One of the interesting things that came out straight away was that the optical spectra photometry, while it had a good shape, tended to be underestimating the true fluxes by about 10%. And for the larger galaxies, that error builds up to 20, 30, in some cases 50%. What this probably is a background subtraction issue. They were using long slit spectroscopy, and they had to move it backwards and forwards, and then they had to measure the background for the edges of their slits. So they were probably getting some galaxy light into their background measurement. At least that's Rob Kennicott's best guess, and Rob knows a few things, so I'll run with that. This error propagates through to star formation rate indicators, which have been calibrated with the H-alpha flux measurements. The H-alpha fluxes need to go up. That boosts the star formation rates, and that's going to flow through to the calibrations of star formation rate indicators that Rob's been doing for the last few years. So star formation rates derived from the radio or from, say, a Spitzer 24 micron using the Mustaka spectra have to go up 10%, maybe 20%. Here's a couple of the spectra that are in the atlas. So here's NGC 3079, which I showed before. The yellow dots are the photometry measured across our bands. And then in white it's the spectroscopy. That's a disk galaxy. You have nice warm dust emission showing up in the pars. You have nebular emission lines. We have some more interesting galaxies. Here's Perseus A. Lots of interesting things going on in the mid-infrared. Very hot dust in this particular object, booming H-alpha, for instance, in this galaxy. one of the low metallicity dwarfs that I was mentioning earlier. Again, booming emission lines, and then silicate dust emission rather than silicate dust absorption, which is it's the only galaxy in the sample that really has this. It's quite an oddball. But, there it is, and nothing in the way of pars, at least nothing obvious. I mean, you normally think
emission in like quasars.
yeah, that's what I normally would have thought, but this is a
Compact star form.
yeah. It's there. JD believes it, so and then here's one of the sort of favourites that's used quite often. IC 4553 or up to 20. I think Casey and I joked a decade ago that we should write a paper about how abnormal up to 20 is.
That's the archetypical Euler.
Yeah, it's the archetypical Euler, and yet it's an oddball in all sorts of ways. Still, because it's the archetypical Euler, it gets used quite a lot. And it also has lots of templates in the prior literature, so it's useful to have a look at this to see how we compare to the prior literature. So for the prior literature, I've taken a bunch of templates from the past, from the previous decade. Because those templates were all updated with Spitzer Spectra, unsurprisingly, around about 10 microns, they're all in broad agreement. However, because the prior literature didn't have the Akari data, you could see that our SED differs significantly from the prior literature in particular. There's this dip at about 3.1 microns, which is believed to be associated with water ice. So this feature is quite big, and it's sufficiently big to affect the broadband colours. So it does matter if you're trying to determine photometric redshifts or model mid-infrared photometry. Even in the optical, there's significant differences between our templates and the literature. Our template is redder than all the other templates in the prior literature. It's redder in the photometry, it's redder in John spectroscopy. But then the real fun is in the ultraviolet, where the prior literature overestimates the UV luminosity of up to 20 by factors of several or orders of magnitude. And the bizarre thing is, up to 20 until relatively recently actually did not have any effective constraints on its UV flux. So Chariot Elbaz do actually mention that there is no constraints on the UV photometry, but that didn't necessarily stop people using their UV SEDs. And I know this because I was on at least one observing proposal that was pointing out that here's a galaxy at high redshift that has lots of properties of ARP 220, but is much more obscured than ARP 220. Of course, looking at this, ARP 220 is in fact much more obscured than ARP 220. So this is why we need template libraries. That said, there's still a lot of work to be done because actually this is an old plot. It's not constrained with 2 photometric data points anymore. I've constrained it now with 3 photometric data points from Swift and Galax, but it's still, sorry.
I have just a question on this on 220. Is this for the nuclear or is this spectrum? Where is this taken?
This is for a pretty large chunk of the entire galaxy. So it's not just the core, it's pretty much an integrated spectrum.
So then the UV will be very different if you're taking core or in line as.
Although looking at the colours, if you took the core, it should be even redder, right? Because the core is where all the obscuration's happening. So I don't think it's merely an aperture. I don't think it's merely aperture bias that's affecting this result. Because the aperture bias would, if other people had smaller apertures, it should be even redder. But it's the opposite.
Yeah, so this is a good case study, so I can ask you a couple of questions. I mean,
Sure.
Certainly the Paletta, I have no idea what Donnelly used for the UV, but it must be very different just overall extinction law compared to what you're doing with the magphys. And but there you don't have, there's no UV spectra, you're modeling the spectral energy distribution with magphys and then calling the spectrum and making sure it matches the galaxy point.
Yeah.
What extinction law then gets stuck in here?
There's 2 extinction laws in magphys. There's one for star-forming regions, and there's a more sort of general star formation law.
Okay, so like Milky Way and the Chaldean table.
Something of that ilk. I can't remember the full details.
You argue the Chaldean law would be very applicable to something with optically thick UV photons.
Yeah.
I'm just curious.
It's definitely two laws, but I can't remember the details. For some of the more extreme ULERGs, MagFizz does struggle, and I had to basically apply a kick to the templates to get them to agree with photometry. So it's still...
It's something like this with silicate optical depth of more than one, it doesn't make any sense at all. Then the UV may not even be absorbed, it's just scattered light, and so it could look really weird.
Yeah,
But, yeah, but-
so all right, extinction laws, one thing. Some of the attenuation laws include the effects of the scattered light. They model some fraction of the light scattered back to your line of sight. I'm just curious to know because this. In the past, these optically thick type things are just a beast to model.
And the MagFizz is still assuming a spherical cow type, a spherical cow type situation. If you talk to someone like Richard Tufts, he gets very angry that, how can people be using derived parameters from such things because it's a spherical cow and you really need to model it on a pixel by pixel basis. Sort of what he would argue, which is impossible and also right, I think.
So, can you say something about how you tie together the spectra and the modeling?
So one thing is MagFizz is really, really good most of the time. So that made it easy. There wasn't necessarily big offsets most of the time between MagFizz and the data. And then it was basically to fill the gaps. Basically, it was just sort of an interpolation. So if there was, if there was something where MagFizz was like this, I just sort of applied a tilt to get it to bolt onto the spectra. Normally, for most of the galaxies, that was a modest thing to do. There are exceptions that are mentioned in the paper, and some of the more extreme ULERGs are amongst those exceptions. The low metallicity dwarves are also among those exceptions, and some of the AGNs where you had to mid-infrared was being messed around with by AGN.
So in creating the model templates, did you just run some huge grid of parameters to get the basic best fit?
That's what MagFizz does. It grinds through a large amount of parameter space to get a best fit. It's a very impressive code, but it is very slow. It's taking about 10 minutes per galaxy. So that up to 20 example shows just sort of the difference between our work in the literature for one galaxy. This sort of illustrates the difference between our work in the literature for the entire sample. So color diagrams again. In grey, the observed colours of galaxies at a redshift slice, and then the synthesized colours from the SEDs plotted in red. Kinney over here on the right, and then our SEDs over on the left. And you can see that we're matching up quite nicely with the galaxy locus. Lots of galaxies here, which is where the ellipticals are. There are some things off here. These are the low metallicity dwarfs again. At the redshifts that we're looking at and the magnitude limits that we have, low metallicity dwarfs are generally too faint to see. So you see these extra templates lying off here, off in no man's land, and that's because those galaxies are too faint to see in this particular sample. They might turn up in deep samples like LSST, so it's something to worry about when it comes to photometric redshifts. There are some Kinney SEDs like this one out here which just don't seem to be matched, and I suspect that's an error in the Kinney templates. The comparison between Paletta and our work in the mid-infrared, so this is for redshift 0.2 this time. Spitzer colours in both cases for a redshift slice of 0.2. And actually redshift 0.2, none of the Paletta templates actually fall on the star forming locus. Here are our SEDs. So reasonably good match here over for the elliptical galaxies. A few templates scattered between the two loci. Here are the star-forming galaxies. There's a good population of star-forming galaxies here. It should be noted that the photometric errors here, particularly on the y-axis, are sort of on the order of that, which is why you see a bit of a spread in the colours up and down from the templates. And then up here we have all the crazy AGNs, which are real objects, and you can see a few objects up here, but they're not particularly common. If we pour these templates into our dumb photometric redshift code, simple chi-squared fitting, nothing clever. You can definitely do better than this with EZ and more sophisticated codes. And indeed, in tests with EZ, we have got improvements with this, with these templates, and this very nasty systematic error disappears, and we get far fewer redshift failures now with these templates. And this is just pouring all of the templates in, no priors, nothing clever, no rejection of bad photometry.
I was going to ask, it's actually impressive that we would work at all, even above Redshift 1, if you think a nearby library. But is there a trend with Redshift? I mean, do you see, because you would expect that from an eCorrect.
Yeah, there is a trend, and the trend that definitely shows up for the red galaxies.
Yeah.
So someone should burn huge amounts of keck time or something to produce a passive template for Redshift 1. In fact, given that luminous red galaxies are quite luminous, you'd think that there might be some data already available if it's been calibrated properly.
Can you remind me, excuse me, can you remind, you say on the left hand there are a lot of those failed fits. Can you just remind me what is the primary reason for you to be able to pull one of those things? Most of those data are great.
It's basically getting the PAH emission right in the mid-infrared. So it's basically getting the mid-infrared spectrum right for star-forming galaxies. Also mixed in with a little bit of getting the normalization right, so bolting the optical and mid-infrared together so there's not some tilt built into the data.
So this photo there, you need all the way to use data all the way to the mid-infrared.
Exactly.
From the UV all the way.
Yeah. So often when people do photometric redshifts with Spitzer data, they throw out the rest frame 5 microns onwards because the SEDs don't match that data. So they ignore the PAHs, which is a pity because PAHs are nice, whopping, big, strong features which produce big changes in colour with redshift, which is normally what you want if you're trying to measure photometric redshifts.
So you're saying this actually, that PAH feature is extremely positive for fixing all this issue.
Yeah.
Right, it's helpful for certain types of galaxies, right? And that's, I was going to ask you, the ones where the photo Z always comes out to be 0 and includes the mid-infrared data with a lot of templates, is that just one type of those star-forming things?
Principally, yeah, I think so.
So in this case, the mid-infrared data does improve the photoses. I mean, if you run your code again, throwing out the mid-infrared data with your templates, what would happen?
It's an interesting question. We haven't done a full range of photo Z tests. It's definitely an interesting question. And there are, you might need to be clever because there's still, some gaps in the mid-infrared coverage. So, whether or not you'd have to apply some weighting scheme in there, that treats some of the wavelengths, some wavelengths being better than others.
I'm not sure. It'd be crazy to combine the templates in some linear way.
Yeah. Yeah. So for instance, one thing is, I've thrown in Perseus A in here, which is an extremely unusual galaxy, and I'm expecting it to generate good photometric redshifts. Perhaps putting a prior on Perseus A, the Perseus A template would make sense. And yeah, certainly these templates have been thrown into easy and it produces better results than the default templates. Just an example of the applications. So one thing is dust-corrected star formation rates. So just taking the WISE 22/23 micron luminosity as a function of dust-corrected H alpha. And here are the original measurements in grey if you don't deal with the filter curve error, and if you don't rescale the H alpha measurements for the fluxes, for the underestimate of the H alpha fluxes that I mentioned earlier. And then if you correct for that, you get quite a big change in the relations shown in the black, and the scatter collapses as well for those measurements too. So one of the applications is revised star formation rate indicators. Another one which was hinted at the start of the talk was galaxy colours. One of my PhD students, Richard Baird, which he produced this about ages ago, I should update it, but basically he's been looking at the K corrections for Sloan galaxies, low redshift Sloan galaxies. And he's determined K corrections by taking the templates and looking at the difference between synthesized absolute and apparent magnitude as a function of observed colour. And when he does that, he gets these really tight relations, often with an RMS that's less than 0.02, 0.03 magnitudes RMS scatter around these polynomial fits. And then when he uses those polynomial fits to determine the K corrections, you get lots of interesting things popping out. So this plot, this two-panel plot shows rest frame mu minus G colour as a function of redshift with the VAGC NYU K corrections on the left and Richard's K corrections on the right. And there's really significant changes in the colours of galaxies here. The rest frame colours of low redshift Sloan galaxies in the main Sloan sample that are magnitude, was it 18 and brighter? R of 17, was it 17.8?
For the photometric sample?
Yeah, for the spectroscopic sampling.
Right.
Yeah, bright galaxies.
I'm sorry, right.
Bright, low redshift galaxies. So, now one of the interesting things when you look at the VAGC colours is as you go up in redshift, this red population appears, okay? And that red population just doesn't exist at redshift 0. And the reason it doesn't exist at redshift 0 is I think this population isn't actually real. What it is that the K corrections for VAGC were determined by fitting PCA components to the photometry at fixed redshift. As you're getting towards the fainter end of the sample, the red galaxies, the U-band data is getting a bit ratty, and you're trying to fit multiple components to limited data. And so what you're starting to get is the colours blow out here. That doesn't happen with Richard's approach, and you get this much tighter red sequence of galaxies, which is gradually changing in colour as you would expect for an evolving stellar population.
So for his, is it, I'm not going too detailed about it, but for Beers, PhD,
Bear.
he's picking from a vested template using that. I mean, you're doing smart interpolation, right? That's
No,
basically.
quite actually, I mean, in some sense, double interpolation.
Double
It's just a
interpolation.
polynomial,
It's not a line,
fit.
so it's smart of the line, right?
Yeah.
So for Beers, it's more of a smooth transition where it gets with take getting funny buckles based on that PCA.
Possibly, yeah. It gets really bad for the LRGs.
Yeah, they're only at the 10 to the magnitude level, but it's an interesting observation.
Also, actually, the blue cloud of galaxies. Our cloud is bluer and broader, and I suspect it's because we're including those star-forming galaxies with strong nebular emission lines that aren't normally included in here. Colour magnitude diagram, again, same story. I'm running low on time, so I'll push along.
Is that our fault?
No. You're supposed to ask questions because I had explicit instructions to be prepared for questions. Samantha Penny has been looking at void galaxies in the Gamma survey. And one of the neat things that Sam has found is if you plot up the colours of void galaxies and compare them to galaxies overall, when you look at the most massive red galaxies in voids, what you find is that their colours are actually offset from the red sequence that you find elsewhere in the universe, in the filaments and the clusters. It's a subtle effect, but it is there. And also most of the void galaxies that she finds, the massive red void galaxies, instead of being passive, they often have N2 emission. So instead of being passive, when you look at the spectra, what you see is N2 in emission, and the spectroscopic pipeline that Gamma uses keeps on calling these liners / AGNs. You also see H alpha being filled in somewhat for these galaxies. So these red galaxies in voids, while they're as massive as some of the massive galaxies in filaments, they seem to have some
properties that are different. If we look at the mid-infrared colours for Ys for these galaxies, in fact, we don't see those passive galaxies. They're all offset here into sort of that transition regime between the passive galaxies and the star-forming galaxies. And when Sam looks at the images, which are a bit ratty because we're looking at magnitude 18 galaxies in Sloan, they look like they're disky, but that's a bit tentative. One nice thing with the SED library is we can look at analogues of these galaxies in the low redshift universe and see what they're like. And what we tend to see is galaxies like this, which have red overall colours, passive-ish looking spectra, but they have N2 emission and filled in H alpha, and that's coming from star-forming bits at the edges, and you see that there's features in the mid-infrared which also suggest the trickle of star formations going on. Some of the galaxies look a little bit more boring, but again you see that there's some action going on in the mid-infrared. So this is a really interesting result. It suggests that void galaxies are systematically different from comparable galaxies in other environments. It suggests that there's something like halo assembly bias, or that the large-scale environment on sort of more than megaparsec scales is directly influencing galaxy properties.
Or didn't influence the algebra. We'll talk about this.
The paper is in press. It's already on archive, and the SEDs are available from a database that's linked from the archive preprint and will be linked from the paper, so you feel free to download the SEDs. You could also download all of the images that went into producing the SEDs. And so I'll just finish up obviously with a summary. 129 SEDs spanning broad range of galaxy types in the low redshift universe, broad wavelength coverage, smaller error than previous templates, and there's a whole lot of science applications that are already starting to flow from these templates, like changes in star formation rate calibrations, quite significant changes in rest frame colours for galaxies, even for low redshift galaxies where you might expect that this sort of thing was nailed down. The preprint is available now. It's going to be published at J Supplement Series in May. And if these SEDs are useful for your science, please go ahead and download them and use them and potentially break them for your own science. Thanks, mate.
More questions?
You.
I'm sorry.
How far out into the mid-infrared do your templates go that you still say are trustworthy?
30 microns. So as far as the IRS spectra go.
IRS Spectra, have you tried, you come up with some kind of thermal dust emission to match the rest of the bands? You may not have that in one case, I guess.
It's in the to-do list. So for reasons of sanity, I stopped at 30 microns. Also, for the original motivation was good photometric redshifts in the Boredes field, so I was just interested in going out to 30 microns. But yeah, lots of people have asked me, when are you going to fold the Herschel data in, etc. So that's in my to-do list. I might do some other science to take a breather before working on Herschel data and extending this out to much longer wavelengths.
So you showed the really nice result when you use instead of K-correct for your templates. Does that kind of close the circle? Does that bring it back that it is perfectly consistent more with the passive evolution you would expect for early tech galaxies?
It does look that way.
There's a tilt to it at least.
Yeah, there is definitely a tilt. I need to cross-check. It'd be interesting to cross-check with a Bruce-Wallen-Charlot model, let's say redshift 1 rather than redshift 0.2. But yeah, it does. Richard has done work with these templates of the Boredes field out to redshift 1, and the tilt is back in there. You don't get the have it running flat.
Yeah, okay. Which you do see is flat there.
Yeah.
Christopher, what if he uses corrections?
He used the Kinney templates, and yes, so that did actually something similar to the polynomial fitting technique. Given that the Kinney templates have systematic offsets and large scatter, you'd expect that to build in significant errors. And then the ultraviolet, the Kinney templates were bolting
optical spectra, I think primarily from CTIO to RUE data, which was extracted by a 20 arc second by 10 arc second elliptical aperture, which may or may not have been pointed in the right direction. There's lots of notes. I tried to look at RUE spectra for this project, and there's lots of times you come across spectra where there's a little note that says this might, this might not be actually pointed at the right, exactly at the right thing.
Yes, this concern. Other questions? Okay, well, I aired previously, Michael is on an airplane at 2:45, so he will not be around much longer. If you'd like to talk to him, do so now or for a piece. There are some goodies in the back, including coffee, things. I would love it if that food would disappear, and I don't know about it. So, we get the container, take it. Okay, well, thank you, Michael, again.